I'm truly honored to be here today. My talk is about sampling of attributed networks from hierarchical generative models. This is a joint work with Sebastián Moreno and Jennifer Neville. What is network sampling? It is the process of using a generative network model to randomly create networks. These are used to represent entities and relations between entities, among entities, using an ordered pair of nodes and edges, respectively. Network sampling is a powerful tool that facilitates tasks such as anonymization of data, hypothesis testing. For instance, we can use random network generations to build empirical distributions in order to perform hypothesis testing. By randomly generating networks, calculating the likelihood of those networks, and then ordering the values and building the empirical distribution. And after that, we can define critical values to perform hypothesis testing, right? There are other tasks like sensitivity analysis, simulation of processes, evaluation of protocols, etc. Because of these practical motivations, many generative models have been proposed to sample network structure alone. However, sampling of networks with correlated vertex attributes remains a challenging problem. Correlation appears due to attributes in the social network, for instance, political views, gender, and others. So to model attributes, networks need to draw samples from the joint distribution of structure and attributes. Here we have in the axis corresponding to G, we have the attributes, the structure, and in the x-axis we have the attributes. Ideally, a full description of the joint distribution consists of the conditionals of the structure given the attributes and the attributes given the structure. However, this task is not always possible to be done. So, despite the shape of the distribution being that complex, the one thing we can do is to approximate sampling. We have two problems with approximation. First, learning, and second, sampling. What corresponds to learning, the main problem is that there is not enough data to perform that estimation. So to solve this, one alternative could be to fit marginals that correspond to the structure and attributes independently, so we can assure that those marginals are good enough. The question is, however, how to put these marginals together. So that's a complex task. When it comes to sampling, the problem is, on the other hand, that most of the space of this joint distribution is sparse, has zero probability. So finding a good model, a good generative model that produces samples from this complex joint distribution, mostly sparse, is a very, very challenging problem. So there are some existing methods that deal with modeling attributed networks, which include probabilistic relational models, ergams, multiplicative attributed graph models. However, although these methods are good in dealing with the tasks they were developed for, they were created for, they have some limitations when modeling the joint distribution. PRMs, for example, they model the network with attributes, but have difficulties that appear in the constraints of the probabilistic model. Ergams can be used to learn features in the network, but sampling is not effective because of the dimensionality. MAG can create a sample of structures, can sample structure, but for that it uses attributes. But these attributes are actually latent attributes, not attributes in the data. So it needs to be modified in order to encode that information. We want to model. We want a model that fully represents the joint distribution. For that, we have two choices of sampling. One is to draw the instances of the structure, G, and then sample the attributes X conditioned on the structure. And the complementary idea, the opposite idea, is to sample attributes X, and given those attributes, we can sample the structure. Whatever the choice, we need to consider the fact that due to the complex shape of the joint distribution, if sampling starts from a region with low likelihood, the search can lead to particular modes from which it will not be easy to escape due to local minimum. So this is a common problem in optimization. Optimization. So the idea then is to use the marginals that were fitted to the attributes in the structure to somehow construct the joint distribution. But in this scenario, the thing is that sampling is not only affected by the shape of the distribution, but it also there are also other problems that I will describe in this talk. In particular, if we sample condition on the structure, then we will have to deal with cyclic dependencies of the probabilistic model, which is a problem in sampling, because it is not possible to identify the right ordering of sampling of attributes in a network. To avoid that, we could instead sample condition on the attributes. And that is actually one technique that is used by an existing method, the attributed graph model, that samples networks condition on the attributes. The three basic steps of AGM would simply, roughly speaking, consist on learning the generative model from data, fit a distribution to the attributes, then sample the structure condition on the attributes, and then apply a rejection sampling on the candidate edges based on the node attributes. So AGM has been tested with marginals that are modeled with traditional generative models like Chang-Lu and its variants, transitive Chang-Lu, fast Chang-Lu, as well as chronicle product graph models. It works well in all these models. However, when applying a hierarchical network model as the structural marginal for AGM, the attribute relations are not precisely captured. And that's a problem of AGM with hierarchical models. So in summary, we have seen that there are some problems with existing models of attributed networks. We saw that some existing models have an inefficient sampling because of this dimensionality, parameter dimensionality. There is also certain inappropriate assumptions in certain generative processes. There are cyclic dependencies in when sampling condition on the structure, and if we solve that problem by conditioning on the attributes, then we'll have to face this problem of sampling from hierarchical models. So the first problem can be solved by approximate sampling using a the joint information obtained from the marginals. The second can be solved by condition on the attributes instead, but again, condition on the attributes then has these problems that arise when dealing with hierarchical models. So we proposed a solution. We approximate sampling using marginals for structuring attributes also. We condition on the attributes, but we additionally adapt sampling to work with hierarchical models. So in summary, the steps of our algorithm consist to sample the attributes from the fitted distribution of attributes, sample from the hierarchical model by first sample edges constraining the structure given the attribute, and then if the attribute relations are captured accurately, then we're done. That's it. The problem is solved. But if not, then we can return to the second step and back up a level in the hierarchy in order to further constrain sampling at that level. Now, in order to understand a little bit more the problem, let us discuss more in detail how a hierarchical generative process works. So we know all generative models like Erdős-Renyi, stochastic Broad models, they are actually not good at modeling real networks because they don't capture the real characteristics. In real networks, we have power law distributions, we have community structure, large connected components, etc. Right? An Erdős-Renyi model has a binomial degree distribution, right? That's a problem. And stochastic Broad models have community structure but don't have power law distribution either. So for that reason, newer generative models have been proposed to represent real networks. For this purpose, some of them use a hierarchy of random variables that reflect dependencies among edges in the network. This allows to bias the sampling of edges to produce skewed distributions, in particular power law distributions, degree distributions with community structure. This produces realistic characteristics in the networks, in the sample networks, but also makes sampling of attributed networks more difficult. So one way to bias the sampling is by creating this hierarchy of random variables that start at the root level, for example, that can be represented with a matrix of probabilities. From this, we can sample blocks using Bernoulli trials and then use the output to only sample subblocks by assigning probabilities inside the blocks that were sampled before, right? In this process, we are sparsifying the sampling process. We disregard the blank spaces, and we perform a sampling that allows to obtain skew distributions, realistic characteristics in the sample networks, but also it can be, in certain scenarios, can be done efficiently. So this process can be repeated until we reach the edge level of the hierarchy. Now, let's think about the implications of this type of sampling. If we consider again the attributed graph model that I described before, imagine we model the structure with a hierarchical model like MKGM, and we apply it to AGM. Well, I briefly mentioned that AGM will not perform well with hierarchical models, but the reason is because AGM assumes sampling using a full matrix of probabilities, while a hierarchical model specifies that matrix. So at the last level of the hierarchical process, we will have a matrix that is mostly zeros. This was proven in Lemma 1, so if you are interested, I can answer any questions offline. So now, in order to solve the problems I described with the existing models, first of all, as in AGM, we are going to condition on the attributes to avoid cyclic dependencies in the model. But in order to solve the problem of sampling from hierarchical models, the algorithm is going to be adapted to deal with this specified space of hierarchical models. For this purpose, we first sample the attributes, and then condition on the value of the attribute, we perform sampling of the structure. For that, we introduce CSAC. CSAC is constrained sampling of attributed networks that consists of two stages of sampling. It replaces the idea is to replace the basic sampling at the edge level with a maximum entropy sampling to constrain the process and consider attribute relations. For that, we exploit the correlation of the attributes, which we denote with rho. The correlation is an important network characteristic that encodes phenomena such as homophily, social influence, etc. Consider a set of edges in the graph. They define a couple of vectors formed by the set of labels of their linked nodes. Labels can be attributes, for instance, 0, 1, female, male, religious or not, conservative or not, but can also be continuous features like height, weight, etc. If we calculate the correlation of these vectors, we have the correlation of the graph that can be alternatively represented with a couple of summary statistics that are types of edges that we denote with psi, and the fraction of edges per type that we denote with beta. They also, again, define alternatively the correlation. So in our analysis, instead of using rho, we will, the correlation, we will simply use psi and beta. Using this information about the attribute relations, we perform sampling of the edges, which is the first stage of this sampling process. This is done by taking both the attributes and the matrix of probabilities, and we take the set of probabilities in the matrix without repetitions, and we summarize that with u, the variable u, and then using, since we know the probabilities and we know the number of trials, we can, instead of performing Bernoulli sampling, we can use a binomial sampling, right? Very simple. But now, the key idea is that we also were able to encode the information about the correlation using this alternative view of the correlation, which was encoded with the parameter beta. So we can use that parameter to sample using a multinomial. And that way, we are introducing attributes in the sampling process to finally obtain the target sample network, which consists of adjacency matrix and the vector of attributes. Notice that the correlation may not be achieved with this sampling process. Why? Because as we move in the hierarchical sampling process, the choices that of combinations of attributes are more and more restricted because the space is more restricted. Think about a fixed network. If you assign particular want to model a particular correlation, it may not be possible in that way. So it's going to be even more complicated when we have a random network, and the process is also sparsified as we perform this hierarchical sampling. For that reason, if the correlation is not possible, then we can, what we do in our approach is to back up a level in the hierarchy and apply constraint sampling using linear programming for that to sample blocks considering attribute relations. Block sampling is the second stage, and what we do is to basically encode the constraints of using a linear program. It's done similar to ME sampling, but works at higher levels. The idea is to constrain sampling so that the correlation is still possible. How we try to guarantee that the target correlation is achievable using this objective function where we minimize the number of blocks for which that correlation is not possible. Now I'll skip the details of these two because of time constraints, but if you have any questions, I can answer it later. Now, what happens if this correlation is not achievable? We can back up another level in the hierarchy and perform a similar process with an LP sampling. Okay, in the experiments, we wanted to evaluate two things, the attributes and the structure. With respect to attributes, we wanted to measure the correlation. And with respect to the structure, we wanted to measure the distribution of characteristics, errors on those characteristics. For the experiments, we used 3 datasets, Cora, Facebook, and patents. Cora is a collaborative network of archive papers where we have relations between collaboration between authors. The attribute that we measure is AI for papers that correspond to artificial intelligence. Facebook has 2 features, religion and politics. For people who have religious views or conservative views, and for patents we have the attribute category. We use 3 models. We compare our method CSAC with AGM, 2 implementations of AGM because AGM is the state of the art in these datasets. AGM with Chonglu and transitive Chonglu, and AGM with MKPGM. First we analyze the attributes. For that we use the correlation. We measure the correlation errors. Our algorithm CSAC, which is shown here in the bottom line, is closer to the original correlation, and the results are statistically significant, which we mark with a star. It's not the best for patents, but it has a competitive performance. With respect to structure, we analyze distribution of 3 characteristics: degree, clustering coefficient, and hot plot distributions. Our algorithm is the best performer also in this. I will skip the details because of time constraints, but in this plot here, we summarize the results of both attributes and correlation. The horizontal axis is the error of the characteristics, measured for the characteristics, and the vertical is the error for the attributes. The algorithms are shape-coded, and the datasets are color-coded. The best performers are to the bottom left, closer to an error of 0, 0. As we can see, our algorithm is the best performer for all 3 datasets. We showed how to sample or model the joint distribution of attributes and structure using CSAC, enable 2-stage constraint sampling of the joint distribution. CSAC is designed to deal with the sparsity constraints of the hierarchical models, such as NKPGM and Bitter, but can also be applied to other models. CSAC's implementations with NKPGM over 3 datasets shows that it produces the most accurate graph samples with respect to both structure and attributes. It maintains the network variability of the underlying network and outperforms the correlation that AGM obtains using the same underlying network model. Some applications of our work include, as I mentioned at the beginning of this talk, anonymization of data, hypothesis testing, simulations for processes that run on top of synthetic data. It can be applied for causality models, analysis of causality models, sensitivity analysis, evaluation of protocols, and other applications. So, thank you very much. I don't know if you have any questions.
So my question is the following. So if you think about a social network, right, there are 2 reasons why you can find correlation. One is because, let's say, homophily, so people are similar and then they become friends. But the other one is, let's say, influence. So I affect my friend, and then he changed, and it looks like say you said you have different ways to do the sampling, right? You can first sample from the attributes and then do the structure, or you can start from the structure and do the attributes. And this, what you see in a network is sort of a mix of both, right? You see like homophily sounds like sampling from the attributes first and then the structure, but influence sounds like sampling from structure first and then the attributes. So how would you deal with these two different cases? Like how would your model capture these two different cases?
Yeah, that is a question that is a little bit higher in the semantic analysis of relations between people. That's a good point. Our model doesn't differentiate explicitly between the two. Our interest was to model jointly both, regardless of whether the correlation is due to social influence or due to homophily. But in order to answer that type of questions, there's a need to modify a little the model so that they can this type of causal analysis can be answered. So our model is a little bit more. So it's model agnostic. It depends on how well your your marginals were fitted to the data. If your marginals are good, are a good description of that relation, then the algorithm will perform well. So it will perform as well as the marginals are a fit for both a structure and attributes. So I don't know if that answered your question. But, yeah.
Any other questions? So can you talk a little bit, because you kind of skipped in the interest of time, about the assumptions of what kinds of correlations and distributions are on the data that allow you to actually do, that lead to convergence in your process?
So let me go to the slide of. Yeah. This is a sampling of edges, right? What we are doing here, the assumption that works here is that the parameter beta is achievable at that level, but that may not be the case. So that's one of the assumptions, but we knew about this, and in order to solve this problem, we have the second stage that verifies whether the correlation was actually achieved. And the reason is that certain values of the correlation will not be possible in a generative model. Certain values of the correlation are not possible in a fixed network. So it's also something that happens in fixed networks. So something similar happens with random processes, random models. Certain values of the correlation will not be possible. So the assumption that we're working with here is that the correlation is achievable, but we know about it, and in order to deal with those cases for which the correlation is not achievable, we have this higher level where we verify whether the correlation is or not achievable. And for that, what we do is to constrain and drive the search through regions of the likelihood function that will allow us to sample networks with the target correlation. So that.
We continue. Okay. Thank you. Let's thank the speaker again.